So let's have a look at different strategies for buffer management. These strategies have to decide which page needs to be evicted if the buffer is full and there's no space, hence to insert a new page. So one of the old pages has to leave. We call this eviction, or we kick out a page from the buffer, basically. Strategies can be classified according to different dimensions. One dimension is time. Do we consider the time since the last insert, since the first insert, or not at all, time at all? Or do we look at the references, how many references have been there, so how many times we wanted to access a page, or don't we look at this information at all? The first idea is very simple. We just do a random replacement. We call this the random strategy. You can already imagine that this is not the best thing to do, but it's very efficient to implement. But it's not the best thing to do because you don't consider at all how popular a certain page is. So you would arbitrarily kick out pages without any information if this page was rarely used, frequently used, most recently used, and so on. So you would just ignore anything, and you can imagine this won't work well in practice. In this illustration, you see the space of possible strategies in terms of the size of the buffer and the number of page misses, or the frequency of page misses in percent. So this is the size of the buffer, and here you have the miss rate in percent. We call the fact that if you want to access a page and it's not in the buffer, this is called a miss. And if the page is found in the buffer, this is called a hit. And if you want to later on investigate how good different strategies perform compared to others, we can also count the hit rate in percentage, or the miss rate in percentage. In this case here you see the page misses in percentage. So what do we see here? First of all, we see our random strategy from before. And as already said, this won't work very well. And you see this is in terms of the page miss rate, also not very good. So it's quite large, the page miss rate. Then you see here the optimal strategy. So if you have what we call an oracle that could look into the future, and you know exactly which pages will be accessed in the future, then you can come up with an optimal strategy which keeps those pages which are useful for the future. This cannot be realized because, we cannot look into the future, right? So this is only the theoretic optimum if you have access to some future workload. But we don't have this. This is also different now, I should say, compared to the different metrics we have seen before, like locality and sequentiality, because now we are at a current time point, t. This is the past, and here's the unknown future, and we want to conclude, given the past of information, which pages have been accessed. We want to conclude which will be the ones we should keep for the future and which are the ones we can eliminate. So we don't have here any huge workload that we can investigate. This is like a live online scenario where we are at a certain point in time and we have to make now the decision which page to evict without knowing what comes next. Yeah? That's different to these strategies or the metrics before we have used to analyze different workloads. Okay, back to this illustration. So the optimal one we cannot really realize because we cannot look into the future. Random is not very good. And this green shaded area here depicts the realizable strategies. And the strategies we will investigate in the next slides are of course realizable because we can implement them. And they have of course some downsides and some benefits depending on the strategy. We will have a look later on. Now in this illustration you see some funny situations because on the x-axis here you see the size of the buffer, and this point here depicts the case that the buffer is as large as the database is. And now you could ask yourself, why is it happening that this one, so the miss rate at this point, is not 0? Well, it's easy to explain, because even if you have a buffer which is as large as the entire database, in the beginning the buffer is empty, you will have some misses for sure. And at some point the buffer is of course full and the same as the database, but at some point you will access a page which was not yet in the buffer, so you have to load it. Well, it stays there forever, but you have to load it. So that's why you have a non-zero initial rate of page misses. This is also called cold start. Here you see what's happening. You have some upper bound of the page misses, because even if the buffer is very small, at some point you will find it useful to have the buffer. So then that means that the page miss rate won't be 100%, even if the buffer is very small. So the first strategy is called FIFO, first in, first out. And the idea is very simple. We somehow keep track about the insertion times of the pages, and we always kick out the page that has been for the longest time inside the buffer. Yeah. So let's just draw some sample buffer. So we have some page A and some page B, C, D, like this. And the gray pointer in this example points to the element, or to the page that has been there for the longest time. So this was the one that was inserted, the oldest insertion basically. And now let's say we have now the page I that is to be accessed. And what do we kick out? Well, we kick out the page where the gray pointer points to. So that means we would kick out A, put here page I instead, and the pointer moves on from the gray pointer to the red pointer, because B is the next candidate to be replaced if we have to access a page which is not yet in the buffer. If we now, in this situation, where the new pointer points to B, we're accessing a page, let's say G. Yeah? Then the access will just get the page from the buffer. Everything is good. The pointer will not move on. If we accessing, let's say B, we just exit it from the buffer. Everything is good. It stays there. But note that this pointer will not be updated to anywhere else. It just stays there. This is different to some strategy we'll see later on that would somehow also include the fact that B was just accessed again and would move somehow B away from this candidate to be replaced next. Here in FIFO it's very stupid, or very simple. B will remain the candidate to be replaced. Yeah? Even if we just inserted or just accessed B. Okay, now we have J coming. Yeah, well, B gets replaced, of course, by J, and the pointer moves on to the next one, right? So this will be the situation, and so on and so forth. Again, if you have an access to some page which is in the buffer, be happy. This is counting as a hit. It's cheap. There's no need to go to a disk. You get the page from the buffer, but these pointers are not moved. That's important to notice. The next strategy, also quite simple, is called least frequently used, LFU. So for every page we have a counter called the reference counter. Whenever this page is accessed, we will increment the reference counter by 1. And then, well, it's quite simple, the page with the smallest counter gets evicted. Yeah? This means that if pages which are very frequently accessed, see the name, these pages will remain in the buffer, and the ones which are least frequently used or referenced, they will get evicted at some point. So it's a quite simple strategy. Now, there's of course a downside here, because if you have had, like some, let's say, minutes or hours or days ago, some pages which have been extremely frequently used, there's a very high reference counter value, these pages will somehow stay into the buffer, inside the buffer, even if they're not anymore frequently used at the current workload. Yeah? So this is not, this problem is not considered here in this very simple strategy. There's also like some countermeasures against this. For instance, you could periodically decrement the counters. So you would have some, I don't know, every so and so many references you will, or minutes, you can then deduct some value from the counters. So then these very high counters will eventually also get smaller. And then there are again candidates to be replaced. But essentially, the approach is very simple, looking at the frequencies. And you see already the big difference of this strategy compared to the previous one, the FIFO strategy. They did not look at all at frequencies of references. And here this is, of course, a total contrast. We would consider frequencies based on these reference counters. Remember some slides ago we looked at the LRU stack depth distribution to analyze database workloads, and now we look at the LRU Remember some slides ago we looked at the LRU stack depth distribution, and now we look at the LRU buffer replacement strategy. The principle is the same. It's based on a stack, and in LRU you're putting the least recently used pages on top of the stack. For instance, if you're accessing a page A, you place it on top, and all the other pages will move downwards the stack. So if you're now accessing a page B, the new stack will look like this. So you have B and A, and if you're then accessing, let's say, C, the stack will look like this, C, B, A. And now, if you're accessing again C, nothing will happen. But if you're accessing A, well, you will find it in the buffer. That's already good. In this case, then A will again move on top, and we have A, C, B, right? And this buffer has, of course, a certain size. So we can fit only a limited amount of pages in. That means if now, let's say the page or the size of the buffer is 3, and we have another page D, which gets accessed next, and D will be put on top, obviously, and A and C and B in this order will follow. But now we see that B, if you have a stack of size 3, will be kicked out. Right? So the new buffer content will be D, A, and C. And now it can happen that we again access B, and B needs to be loaded again to buffer. Well, this happens, right? So we have B, D, A, and C gets evicted from the cache. This is the principle. What we usually do when we analyze such strategies is to keep track about the number of misses and hits. A miss is the case when we want to access a page, and the page is not in the buffer, so we have to load it from disk. A hit means that we found the page in the buffer. Note that for LRU, if you find the page in the buffer, you still have to make sure that you're moving it up to the top position of the stack. What happened also here in my illustration. Now a bit more complex example you see here on the slide. So we have this sequence of accesses. And again, because for space reasons, assume a quite small cache of size 3. Yeah. So if you have now this situation, and let's walk through that once. So we have A, B, C, D, A, and so on. So we have, the beginning is quite simple. So we have A, of course, and then we have BA, and then we have ZBA. So we are currently at this position here, right? So this we have seen already, ABC, and the stack contains just the reverse order of our accesses. And now the buffer is full. So if you're inserting D, then C and B will remain in the buffer, but move down, and A gets evicted. Now, let's keep track about the hits and misses. And we have previously already made access to A, B, and C. And these were obviously misses, A, B, C, because the buffer was initially empty, so we could not find them in the buffer. And D was also a miss, because, D was not in the buffer, right? but now D is in the buffer. So we are currently here, this one stands for this time point of having access D. And now we go on and insert, or we want to access A. Well, we see A is not in the buffer. So that means we have to access it. So now this is now 5 misses, but then A gets on top. So A, D, C, right? And now we access C. Well, C is in the buffer, that's good, so we have a hit. And C is moved up. This is important. So you see, compared to FIFO, here it is reflected that C was again accessed. So the least recently used ones are staying in the buffer, independent of the time of the first insertion. So next we're accessing, so we're currently at this point. So next we're accessing A, also a hit. So then we have A, C, and D. Then we're accessing B. B is not in the cache, so we have a miss at this point. And we have B, A, C. The next B and the following B, they are all considered to be hits, because we have seen we have B in the buffer, and we also don't have to change the buffer because B is on top already. The next one is C. Well, C is in the buffer, so we have to move it up. C, B, A, and this counts as a hit. And then we continue, of course, and having to access D. D is not in the buffer, so we have a miss, and the buffer content is D, C, and B. And then we have A as last one, and then we have, of course, A, D, and C, and we have another miss. Yeah? So this is how the buffer looks like after the sequence of page references. And now the question that is here asked is, if you're accessing page E, which of these needs to be replaced? And now, as we understand how this approach works, it's easy to see that, of course, C has to leave. So the new buffer content after E gets accessed will be E, A, and D. Yeah. So we could have told this already right away, because if you're considering the name least recently used and the principle, you saw that the last 3 pages were C, D, and A. So among them, which are in the buffer, the one that is least recently used was, of course, C, because among these 3, this is the oldest reference. Right? So C gets replaced with E, and the buffer content is E, A, and D. Let's have a look at a bit more theoretical view on this problem. So whenever we have a page reference string, and the references are denoted with R1, R2, RT, and the subscript here denotes the time, so we have time t currently. The notation is the following: if in the string we look at one time point, that means there was a page access at this time point. For instance, here would be page P accessed on time point RT, or on reference RT at time point T. So let us consider or assume that every page P has a certain probability to get accessed as the next page. And this probability is called BP. That means if you're standing at this time point here, at time point T, looking at the time point T plus 1, we know for each page what is the probability that this page is accessed at time point T plus 1. That means the probability that the reference RT plus 1 equals P is exactly this assumed probability BP. Right? Of course, in principle or in practice, we don't know this. We don't know these probabilities, but let's just assume we do. And the question now is, how many accesses or how many references in this page reference string in the future do we see before we again have a reference to page P? It is kind of obvious that the higher the probability is for a page to be referenced next, the fewer steps we see between the next reference, between now and the next reference. So if you're looking at this, we can specify the expected number of accesses between the next reference to P by the inverse, by 1 divided by BP. Right? So this looks a bit funny right now. Why do we look at this now? But there's a very strong connection between this theoretical view and how LRU works. The time between two accesses to a certain page is also called inter-arrival time. And this is exactly this 1 divided by BP. Now, if you're standing at a certain time point t, and you have seen accesses to other pages in the past, so this is the past and this is the future, and we don't know the future, obviously, and then you have to now decide which pages do you keep from these pages in the past. And of course, you want to keep those that will show up in the near future, over those which will not happen to be accessed in the near future, but later maybe. So you want to keep the ones with the smallest inter-arrival time. That means you want to keep those with the highest probability of being accessed next. What does it mean? Well, if you have seen how LRU works previously, we would keep pages which are accessed in the recent past, for instance A and B and C, but maybe not F, which was long ago, right? And LRU is approximating this inter-arrival time by the time of the last appearance in this reference string. That means we would take this time between the previous encounter in the page reference string and just assume this is also the time it takes for the next occurrence. Yeah? So the LRU principle is based on this observation to keep those which are highly likely to appear next, and so it's exactly this modeling of this inter-arrival time done by LRU. The FIFO strategy we have seen earlier was very simple. We have illustrated this using a ring buffer, and the oldest page, that means the page that is longest time in the buffer, would get eliminated. The downside of this was obviously that even the page has been there for a long time, it might still be frequently accessed in the recent past and should not get eliminated. So what clock is doing, as you can see here, is introducing an extra information into the buffer, a simple bit which is indicating if the page was recently accessed. So let's assume that there's a page A at this position in the buffer, and there's the bit set to 1 because A got recently accessed. So the gray arrow here, like for the example with FIFO, points to the next slot that needs to be investigated if the page stored in this slot should get evicted. But since we have this bit 1, we will not kick out A immediately, but we will note that A was already a candidate to be evicted, but we did not evict it yet. And we indicate this by setting the bit from 1 to 0. Right? And then we move on because we did not find a slot where we could evict a page, and we go on here. Let's say there was page X, and the same situation happened because of this 1 bit. We are not able to eliminate X, so we have to move on searching for the next slot that we find of a page that can be evicted. So this pointer moves on, But again, here for this x, we will set this bit to 0. And then we could look at the next one, and let's say there was page h. And again, there was the bit 1, so we cannot eliminate h right away, but we will set the bit to 0 again. And finally, we come to a position of a page, let's say d, and we see that this bit here is 0, and this indicates that d was not very recently accessed. And now we found the victim. Now we can eliminate d from the buffer and insert our new page that we wanted to load from disk. And let's say this new loaded page was called y. So we will insert y, and of course we will mark with the 1 bit that this access was recent. And this is a big difference to FIFO, because FIFO would not really care about these recent accesses, but clock does. The bit, as the name suggests, can be only 1 or 0. So what you're doing a search like in FIFO, or like cyclic traversal. In FIFO you would always eliminate the oldest one, but here you are not immediately evicting the oldest one, because there could have still been an access to the old one to make it a new one again. So in this bit 1 means it was recently accessed, and 0 means it had already been investigated to be kicked out. So it has another chance. So we will continue our search. At some point we will come back to A, and A, remember, was set from 1 bit to 0. And the next time we come here and we visit the position of A and the bit is 0, then A gets eliminated. It has one chance to be again accessed, so the bit would be put to 1. But if the A is not accessed anymore and the arrow, the traversal, comes back to A and we see the 0 bit, then A gets evicted. So this algorithm is also called second chance. It is important to note that if a page is in the buffer, so let's say, we have this situation here. So A is in the buffer and it has a 0 bit, doesn't really matter now. So in case there is an access to page X, let's say, then, we load X from the buffer, but there's no movement of this pointer here, of the eviction pointer. But it's important that if we're accessing X and X had a 0 bit, that we're setting this 0 bit to 1, right? So these bits always indicate if there was a recent access. And the cyclic search through the buffer gives every page another chance by setting a potential 1 bit to 0, but if it was 0, it gets eliminated. That's the clock algorithm. You see, it's a fine, like a little change to the FIFO strategy, but a very meaningful change. So if a page gets over the time regularly accessed, it will remain in the buffer because the bit will be always reset to 1. And if not, and the arrow, like this traversal, visits the page again, it's getting eventually eliminated. Right. And that's just another illustration of what I have already told. There's a more complex example here you can walk through. Basically, initially, I can say a few words here. Initially, the buffer is of course empty, and this is the arrow pointing to the next element. And we can consider like a buffer, a cyclic buffer, so it will always walk around like this. So we insert C, and these are the bits here, and C gets inserted, and of course we will put a 1 bit there, and then B gets inserted, and you see this is always pointing to the next position to be checked for replacement. Now this is boring in the beginning, but now we have the buffer being full of C, B and D, and these red colors here indicate, the red font indicating that there was a buffer or a page miss, and green means there was a hit. So now the next access would be D in our sequence here, And D, well, D we find in the buffer. So that means that here nothing happens. The pointer is not moving. It stays where it was before. D gets loaded. We are happy. There was a hit. No miss. And we continue. Now the next one is C to be accessed. And C is also in the buffer, so nothing happens. So you see also that here nothing happens in terms of the bit, because it was 1, it will remain 1, right? So nothing happens. And the next one to be accessed is E. And after E was accessed, so we see it was not in the buffer, now it is in the buffer, and now the buffer has a really weird look. And you might be puzzled a bit for the first moment, because it has really changed a lot. So the bits were 1, 1 for B and D, now they're 0, 0. C has been eliminated, right? And E has been inserted. Well, that E was inserted with the 1 bit, that's kind of clear, because it was they just loaded, so it deserves to have this 1 bit. But what happened here? Basically what happened was that we had this situation here. So the pointer pointed to C to be the candidate to be checked for eviction, but we could not evict it, so we just set this bit to 0. Then the pointer moved on. Then we set this bit to 0. The pointer moved on. We set this bit to 0, and then the pointer moved back, like because it's a circular, like a ring buffer. And then we found now the victim, because C has now a 0 bit, and then this one gets evicted, right? And then E gets inserted. This is now this situation, and this pointer points to the next one to be a candidate for eviction, right? So many things happened here between these two cases, or these two situations. And this is also like here a difference noted to LRU, because we see that C was eliminated. Also, the last access to C is more recent than the access to D and B. And in case of LRU, the B would have been replaced and not the C. Why is this? Well, we are at this point in time. We are loading, or we want to access E. What were these 3 pages we have accessed previously? Well, C, D, and B. So among C, D, and B, obviously the B is the oldest one, so LRU would have been eliminating this B, but here in clock we eliminate C. That's a difference. So here you see additional text. This is exactly what I have also walked through in the previous slide, so you can read that again if you want. There have been proposed also different extensions to clock, and what we will see here is the so-called generalized clock. And as the illustration here already tells you, we are allowing to have now reference counters and not anymore single bit. So you have a 2 here, as you can see. Before it was only 0 and 1s. And it's the same as in clock. We do a cyclic search to find the victim to be replaced. And when doing this, when we visit the page and there is a non-zero counter, we do not evict the page, but we decrement the counter. And at some point we will come to a page where the counter is 0, and then we replace this page. Right? It's very much the same as if you understood clock, then this G clock should be very natural following. And now there are multiple options how we can configure clock or G clock. So we can say when we inserting a certain page, for instance, we would insert now page, I don't know, X here, and then we can decide, do we give it a 1 bit, or do we give it like a 1 integer, or do we give it a 10 or like a 20, and how we can make different reference counters here as we want. And then also the other option is, So let's say we initially put like a 6 here, and then over time it's getting lower and lower because we have revisited x. At some point it might be only 2 anymore. So, and now x gets again referenced, and of course we will find it because it's in the buffer. And now we can say, do we increment it by 1 or do we increment it by a larger number? So for instance, we can say we increment it by, let's say 4, right? Or like 4. So then we have 4 plus 2 is 6. So then the counter will be not incremented by 1 as in the normal clock, but here we can have different configurations that allow us to be flexible, and depending on the workload we could find an G clock which is performing best. If you're looking at this a bit more formally, there are 2 different variations that we can think of. One is called version 1 and the other is version 2, obviously. And they're configured like this, or they work as follows. So if we have v1, we say that, well, if it's a first reference, so it's loaded into the buffer, we will instantiate or initiate the counter by a certain constant. Yeah? And for every new access to the page, when the page was still in the buffer, we will add another constant w. Or version 2, the same, we will initialize this page with a certain constant e, and whenever a new reference comes, whenever we access the page again, which is in the buffer, we will not add any reference counter, or we will not add any value to the reference counter, but we will set it to one constant. So it's not adding up, it's just like setting it to a constant. And now you see the subscript, perhaps confusing these I subscripts here. They just take care of the fact that we might want to have different constants for different types of pages. For instance, we have pages that are pages belonging to a B-tree index, or like simple data pages, and depending on one or the other, we might want to have a higher initial reference counter, or maybe going for version 1 or version 2. If we look for or how this is resembling the basic version of clock, if we're setting in clock, or in the previous version of clock, in the very initial one, we had this 1 bit at insertion, and we would always reset it to 1. We will never count it up, right, or sum it up. This means this is like the version that corresponds to the initial clock if we are putting a 1 here and a 1 here, right? Because this one is not the same, because here we will keep on incrementing at every reference. This has a little bit of a spirit of least frequently used, because here you would count the references. Yeah? But again, as opposed to least frequently used, we would also decrement because of the cyclic search in the ring buffer. So it would not have the problem LFU would have. The next one is a very famous approach. It's basically a modification to least recently used, where we consider the last k occurrences of a page access. So in LRU we would always look what was the latest time when the page was accessed, and here we look at the k's last reference. This allows us to distinguish between frequently and less frequently accessed pages. And here's the paper, which is very well written. I suggest you want to read it up, look it up for the first few pages at least. This is like also a good overview for the general topic of these replacement strategies. So basically what LRU is defining is called a backward k distance. So if we have like a page reference string as before, so these are accesses to different pages, so the same pages again, then we're defining for one page P the backward k distance to be the distance to the k's most recent reference. So if we have a page A, and A happened here, and here, and here, let's say, and k would be 2. So we would look for k, if this is the current time point, we look at the last 2 encounters of this page A. So formally, we define this backward k distance to be x. If this the current time point t minus x, so x is also like an integer, a time point, so t minus x was also an access to the page P, and there are exactly k minus 1 references between the current time and this time that we just defined, t minus x. It can of course happen that there were not enough accesses to this page P in order to define this in a meaningful way. So there would not be, let's say, 5 accesses to the page. In this situation, we define the backward k distance to be infinite. And then, not surprisingly, because now it's the same principle as before in LRU, just that we go a little bit more into the history, to the past. Now we define that we replace the page with the largest backward k distance, so its largest value. Right? And if we have in some point many pages that have an infinite one, we can again apply another strategy to distinguish between multiple pages with the same value here. For instance, we could go back to LRU or any other strategy, or just randomly kick out one page. So that's like important, for practical purposes, important modification to LRU. This also avoids the problem if you have like a large, let's say, the table, and you would access the whole table, and then the LRU in the basic version would contain now only pages from this table, and this means that all the buffer content, if the table was large, is now filled with these pages, and it does not reflect the real workload to the database systems in terms of useful pages to be stored. In LRU-2, let's say, these pages would have, if they're accessed only once, they would have like a infinite backward k distance. That means they would be being replaced by themselves with high likelihood, so they will not fill up the entire buffer. In practical terms, usually LRU-2 or 3 is used, because also the bookkeeping is getting quite more complicated, as you can imagine, if you want to implement that and run under very high workloads, or performance workloads. Additionally, LRU-K keeps history also for those pages that get evicted from the buffer. Yeah? For instance, we take additional information storing for every page the accesses from the last 5 minutes. This reflects the 5-minute rule that we have mentioned earlier, and avoids the problem that pages which are kind of frequently used in this 5-minute window get reset to 0 if they get evicted from the buffer. Again, I recommend to look at this initial paper. This is specifically in section 212 mentioned. So now we have seen quite a bunch of strategies, right, for buffer replacement or buffer management, and we can go now ahead and say which are the how can we classify, or how can we group these strategies into categories. In the very beginning, we mentioned that there were 2 criteria that can be used to classify these strategies. One was the references. So if you look at not at all information about references, or only the last reference, or all references. And there was also the dimension of time, so the age of these references. And it's kind of clear if you're ignoring any time information, and you're also ignoring anything about reference counts. So you would be here in none and not. And then with strategy you would not use any information. That's of course the random strategy, right? It would be totally random and not using any information. If you're looking at this box here, so you would not look at the references, and you only look at the time of the first insertion. It's FIFO, right? Or if you're looking at all references, so the count of all references, but not looking at any time information, so you're looking only at the frequency of references, and not at the recency. So now it should be pretty clear what we have to put here. That's the LFU approach. Yeah. And this is now how the table looks if you want to fill it in completely. So I hope you understood the main concepts, and specifically how these methods work. There will be usually exercises and also exam questions that we have. We give a page reference string, and you have to we have to count the misses and hits, or to say what is the status, or how does the last state looks like of the buffer after all of these accesses and so on. There's like very simple ones and also a little bit more complicated ones. I think they should not be very complicated after all, but certainly this one is a little bit more evolved, or clock is more complicated than, of course, FIFO or LFU or RAND. But the more information they have, they're getting also more complicated in terms of implementation and runtime. So what I mentioned already, the LRU-K would not be run with LRU-100, let's say. That would be LRU-2 or LRU-3. But of course it has major benefits compared to a random one, or FIFO or LFU. Also LFU had downsides, obviously. So if you have some historically very, very frequent pages, then they would remain in the buffer, so you have to somehow fix it. You have to do some periodic decrement. But then if you're looking at what clock is doing, they're doing kind of a decrement. In the basic version, it's only a second chance, but if you're going to G clock, you see that this decrement or the increment is happening like in LFU. So you're counting, at least in the version 1, and you're also decrementing. Decrementing is done based on this pointer movement, the search process, the circular search inside the buffer. Yeah? And of course, don't forget why we at all do buffer management, because of this big gap between the time it takes to access data from memory as opposed to taking or loading data from disk. Right? So we have to have a good buffer management, otherwise many times we have to pay at least 10 milliseconds to retrieve a single page from the disk, which is of course really expensive. For reasons of completeness, I want to also mention there is also the task or research done on algorithms and index structures to find pages inside the buffer, which sounds like always easy because you say it buffers in memory, it's very fast, but still there's a difference if you have, let's say, LFU and you're ordering pages based on the frequency, or you're eliminating them. How do you find them, right? So there are different search strategies for the different replacement strategies, or for all, of course, like direct search, and also ones that have additional data structures like sequential, sorted or unsorted lists, linked lists, and so on, or hash tables. But we will not go into detail here. I just wanted to briefly mention that there's also this to be considered. Then last, on this buffer part, a little outlook. I mentioned already when we talked about this two-tier hierarchy having buffer and disk, that there are certain issues with that. So if you have a page which is updated in the buffer but not yet on the disk, and the buffer gets eliminated because of a system crash, the memory is gone, the system starts back up, how do you make sure that such changes are also propagated to disk if user was promised that the transaction they have executed was successfully done, right? So all of these implications on redo and undo, how we call that, is coming up in a chapter on recovery in a few weeks.